Welcome back. We're continuing on. We've got delta G now. Remember, delta G is this thing we just defined just because we felt like it as H minus Ts. But what we found was that it was related directly to the entropy change of the universe. And we found that when delta G was negative, a reaction was spontaneous. When delta G was positive, a reaction was non-spontaneous as written. And we said, hey, it was actually spontaneous in the opposite direction of how we wrote it. So now we need to figure out how do we calculate delta G, and we can do that using delta H and delta S. So we can do that using things we look up in a table, and we can figure out reactions that we don't know off the top of our head, if it's spontaneous, just how spontaneous it is. So we're going to do a reaction, a very simple one. N2 gas plus 3H2 gas goes to NH3 gas, and there's two of those there. And what we're going to do is we're going to look up delta H values. We're going to look up S naught values in our table. These are going to be in kilojoules per mole. These are going to be in joules per mole Kelvin. And let's just go ahead and look those up. Now, we know N2 and H2, the H of formation, enthalpy of formation, because it's 0. Yeah, you're right, 0. Why is it 0? Because enthalpy of formation is how much energy does it take to create that element from its elements in the standard state. And nitrogen is an element in the standard state, so it doesn't take any energy to create it. We can look up this other one. It's minus 45.9. And then we look up our entropies. Are any of those going to be 0? Hopefully you came up with no, because entropy is a calculated quantity. We know it exactly. It's not a change necessarily. We can calculate change in entropy. But it's always K natural log W. W is greater than 1, so entropy is non-zero. 191.6, 130.6, and 192.7. So if we want to calculate delta G, which is delta H minus T delta S, and again, right, these are all for the system because we didn't put any subscripts in. What are we going to do? We're going to just go ahead and do products minus reactants for our H, products minus reactants for our S, and we are good. So delta H of our reaction is going to be 2 times minus 45.9 minus 0 minus 0. And that's going to be, excuse me, a minus 198.0 kilojoules per mole. And our delta S of reaction, here we have a delta because we're calculating the change, products minus reactants, 2 times 192.7 all joules per mole Kelvin, and I should put my units up here, kilojoules per mole on this guy, joules per mole Kelvin minus, and we got the sum of 191.6 plus 3 times 130.6. And when I do that, I get a negative, oops, I copied the wrong one. 2 times 45 is 90, not 98. Okay, so that's minus 91.8 kilojoules per mole. And this is minus 198 joules per mole Kelvin. We're going to convert that into kilojoules. Why? Because delta H is usually reported into kilojoules, so it's minus 0.198 kilojoules per mole Kelvin. And we've got delta G equals delta H minus T delta S. And remember, this one over here doesn't always have the little circles on it to tell us we're in standard states, because it doesn't matter. It's always true. So it is also true at standard states, so we're just fine. And then we take that and we say, oh, minus 91.8 kilojoules per mole. And no temperature information was given. But because no temperature information was given and we have all of these things we calculated at the standard state, it is a safe assumption to say that we're going to be at room temperature. And so it's going to be minus 298 Kelvin times minus 0.198 kilojoules per mole Kelvin. Looks something like that. If you plug that into your calculator, hopefully what you get is a minus 32.8 kilojoules per mole. So is this reaction spontaneous? Delta G of reaction is less than 0. That makes it spontaneous, because remember, it means that the entropy of the universe increased. And so we are all good. All right, so this means a spontaneous reaction. All right, So we can do it, right? We can calculate these delta H's, we can calculate these delta S's, and then we can calculate our delta G's. But quite honestly, it's a little tedious. Wouldn't it be nice if we could just calculate delta G's directly? And the answer is we can. Oh, thank goodness. So it turns out we can look up delta G knots of formation. Now, these are delta G knots of formation, which means, again, they are referenced to a standard state, when the standard state is elements in their standard state. So just like with delta H, they tabulate these things. If you've got an element in its standard state, the delta G of formation of that element in its standard state is going to be 0. But the other ones we need to look up. And so we're going to look up the delta G of formation for NH3. We just calculated it, and we said, hey, that was minus 32.8 kilojoules per mole. But if we look it up in the table in the back of your textbook or in the reference section that I give to you, it says it's minus 16.4 kilojoules per mole. So who's wrong, my calculation or the book's calculation? And it turns out that neither of us are wrong, but we actually didn't calculate the same thing. If I look back at my reaction, I calculated the delta G of formation of, the delta G of reaction for this reaction. And you'll notice that it's forming 2 moles of ammonia. By definition, all formation reactions form 1 mole of product. So here we're saying we get 32 kilojoules per 2 moles of ammonia, which is the same thing as saying in this formation thing that we look up in the back that we get 16 kilojoules per 1 mole of ammonia. So there's no problem here. Okay, so we do have to keep those kind of stoichiometries in mind. I mentioned that in a previous video, but it is important. Formations are always for 1 mole of product. That's why we have to do all that stoichiometric work when we calculate these things. All right, so we can't measure delta G because it's based on delta H, so we do use these formation constants. And so if we wanted to do something like 2CH3OH and 3O2 gaseous goes to 2CO2 gaseous plus 4H2O gaseous. We can go ahead and actually just look up delta G knots of formation in a textbook, so in the appendices that I usually give you as part of tests or quizzes, and we get these values. For this one, it's minus 163. O2 is 0. Why? Because we're talking about formation enthalpies. Now, formation gives free energy, so for elements, it's going to be 0. And our CO2 is minus 394, and our H2O is minus 229. So if we want to calculate delta G of reaction, it's just going to be products minus reactants. 2 times minus 394 kilojoules per mole. I don't think I put my units here, kilojoules per mole on this guy. And then we add 4 times minus 229, and then we subtract off the sum of 2 times minus 163 plus 0. Don't have to worry about the 0 too much. Plug that into your calculator, and you're going to get minus 1,378 kilojoules per mole. And boy, if that reaction isn't very spontaneous. It's a very large number for a chemical reaction. 1,000 kilojoules per mole of available energy to do useful work with. That's what we said about delta G, as it measured that. All right, so we were able to get that information, tell that this reaction is spontaneous, which we expect, right? It's the burning of methanol. We expect that to be very spontaneous, and it is. Okay, so that's how we can calculate delta G more directly, is just looking up delta G formation values in tables, but we can also calculate it from delta H and delta S, or an S, if that's what we have available to us. So it just depends on what you have. All right, the same rules as before. Remember when you talked about Hess's law? And it just said if you have reaction 1 and reaction 2, and they have delta H1 and delta H2, that reaction 3, which is reaction 1 plus reaction 2, is going to have delta H1 plus delta H2. So when you add reactions, you add their delta H's. The same thing works for delta G's. So delta G1, delta G2, this is going to be, well, they're unequal. It's delta G1 plus delta G2. Okay, so same thing's going on. You add these Gibbs free energies. If you reverse a reaction, if you take A goes to B and it has a delta G naught 1, then B goes to A is just going to have a negative of that. Right, so the negative when you reverse a reaction. If you multiply a reaction by a number, so I've got 2A goes to 2B, then I have 2 times delta G naught 1. Okay, so all the same rules you did with enthalpy also apply to Gibbs free energy when we're trying to calculate it. And so we can use it in a number of circumstances. We can use it to find unknown values of Gibbs free energy. We can use it to find the overall Gibbs free energy. So we're going to do a couple examples next where we do those. All right, I think I did 2 slides by accident. There we go. What is delta G for the reaction at 298 Kelvin when we've got iron 3 oxide reacting with hydrogen to make iron and water? So we've got a table there of delta G's of formation, and we're asking you to find the delta G of reaction. So go. Okay, what'd you come up with? You came up with a number. Okay, how did we get that number? Products minus reactants. Right? Why are these 0? Because we're talking about formation, right? Always from elements in their standard state. So these are elements in their standard state, so they're always going to be 0. And so this one's actually pretty easy. We're just going to take 3 times water and subtract 3, not 3 times hydrogen. We're going to subtract our iron oxide. So delta G of reaction is going to be 3 times minus 229 kilojoules per mole minus minus 740 kilojoules per mole. Okay, make sure you got that double negative in there, and they cancel out, so you end up with positive. And if you plug that into your calculator, you should get 53 kilojoules per mole, positive value. And you get this one here. So is this reaction spontaneous at standard conditions? And the answer is no, because when delta G is positive, it means it is not spontaneous at standard conditions. In fact, the opposite is more likely to happen. Iron's going to react with water to make iron oxide and hydrogen, which is kind of a little more what we expect, right? Is we expect iron to rust, not unrust. Right. Our next one, we're going to try to find out what the standard Gibbs enthalpy of formation is for SF4, given we know the reaction standard Gibbs free energy and something about one of the other things at 298 Kelvin. So you're going to try to figure out what is the delta G of formation of SF4. So what did you come up with? Aren't you tired of me saying that? I'm kind of tired of me saying that. I'll have to find a new phrase. What did you come up with? That didn't work. So we have delta G of reaction is going to be, right, we've just got single things here. I didn't put F2 in the table. Why not? Because its delta G is 0. So I don't even need to put it in the table because you know that. Hint, if you ever see something missing from a table, it might be because you're supposed to know that. Okay, so delta G is going to be the delta G of formation of SF6 minus the delta G naught of formation of SF4. And so we just plug in what we know. Minus 374 kilojoules per mole is equal to SF6 we know is minus 1105 kilojoules per mole minus delta G naught of formation of SF4. And you go ahead and solve that one. And when you solve that one, what you get is minus 731. So delta G naught of formation of SF4 is minus 731 kilojoules per mole. And so we go over there and we circle B. All right, so these calculations of delta G are very similar to calculations you've done of delta H. And so if you just kind of try to remember that, they're not as scary as they need to be. Delta H predicted heat, right? It was heat and enthalpy were the same thing at constant pressure, which is what we often experience, but delta G predicts spontaneity. And so we're actually able to say, because this one has a negative delta G overall, right, not of the specific product, but over here, the overall reaction delta G, we can say this reaction is spontaneous, and SF4 should react with fluorine to make SF6 spontaneously. So that is what we are doing with delta G. The next thing we're going to explore is how can we make this even more useful by relating it to other things. Thanks so much for listening. Have a great day.